G'day, everyone. Welcome to Lubrication Experts. Today, I've got a really good interview planned. We're going to do a bit of an international interview today. So I've got guests spanning the globe. So I'm obviously here in Australia, but we've also got South Africa as well as the US. So juggling time zones has been a little bit interesting for this one, but we will press on. But I've got two good experts in the field of open gear lubrication who are here to talk with us about one of the more, let's say, unique lubricant applications. And I think there's a lot of interest that we can delve into, particularly with what makes open gears unique versus, standard industrial and automotive gear sets. So today with us, we've got Laurence Davies. So he works for Whitmore International. And we've also got Bret Jenkins, who works in the Whitmore Shell joint venture. So fantastic to be able to have two really awesome experts to be able to share their knowledge. So, gentlemen, thanks very much for joining me.
Thanks for having us, Robert.
Thanks for having us.
Just to get started, I think it would be helpful to maybe set a bit of a tone, because there'll be people in this audience who are maybe unfamiliar with open gearing, and or if they are familiar, they just think of them as being very, very big gears. So could we maybe set the tone for the discussion to give people a bit of context on like how big open gears really do get, even rough numbers around like sort of power and torque, and what are the typical applications that we might see, or even the actual type of gears and gear teeth that you would see in a kind of a typical configuration.
So I think when we're talking about open gears, and specifically for mining, we're talking about two distinct applications. You've got mills and earth moving equipment, so drag lines and shovels. When I'm talking about sizes, you could have a open gear pinion as small as 6 inches in diameter, clear up to 100 feet, so 33, 35 meters on a drag line swing gear, because that's really just a big bull gear that's swinging a drag line. Drag lines weigh upwards of 20 million pounds. The open gear on the propel mechanism, for instance, picks up that machine and moves it at feet at a time. So you've got extraordinary pressures, big gears, mostly slow moving gears, and you've got to protect those gears with different types of lubricants.
Yeah, a little bit about open gears on ball mills, and it's not just ball mills, it's any rotating vessel. So consider a rotating cylinder as a grinding ball mill, but we also get into kilns in the cement industry and into calciners in other industries where material is being dried through a calciner. So these are rotating vessels of very different size that are rotated by an external stroke open gear and driven by a pinion. These cylindrical pieces of equipment generally turn in one direction only, unlike the mining equipment, which would rotate backwards and forwards, left and right, whereas mill gears and open gears on cylindrical vessels typically turn in one direction. The sizes vary significantly, so grinding mills are very much designed depending on the material that is to be milled, the type of ore, the type of rock. So it's very dependent on the mining operation. We really talk about the power or the drive capacity, let's put it that way, to drive the mill. So it's normally expressed in megawatts. So a very sizable ball mill, that would be a big ball mill, could be as big as a 32 megawatt ball mill. So the more the megawatts, the more that indicates the load that is passing through the ball mill. And also those ball mills can be a lot smaller, down to 5 and 6 and 8 and 10, upward to 32. So a range of sizes in ball mills, depending on the mining operation, what is being milled. If one looks at the cement industry, if anybody's been to a cement plant and seen a kiln is probably 100 meters long or even longer than that. So that has to be turned and rotated by an open external gear. Again, temperatures, load are all things that we need to consider. The girth or the diameter of an open gear on a mill can be 10 meters. The width of the gear can be 60 to 80 centimeters as well. So it's again, many sizes of mill and open gear depending on the application.
Yeah, that's really interesting, and I think that sort of helps frame the discussion. Um, Maybe the next obvious question would be, how do some of those factors make the lubrication of open gear sets unique relative to, other industrial gearing? Like, is it just we're taking industrial gearing and making it much bigger? What makes these kind of gear sets unique?
So it is that, but it's also in a gearbox, you've got a contained gear set and it's surrounded by gear oil typically, right? So gear when you start talking about the fundamentals of lubrication, which most of your viewers will know, you're looking for a dynamic full fluid film. Well, in open gears, obviously there's no fluid. So you're working with boundary a lot, um, especially on the dirt moving equipment, because those gears are moving back and forth. Whereas on a mill, they're always going one way and really um, going a constant speed. There's some newer technology that works in open gears that you're really looking to get that full fluid film in an open gear dynamic. And I don't, both Laurence and I've had a lot of experience on that. You're using super high viscosity lubricants that are, you're in the range of starting out at maybe 12,000 centistokes at 40 degrees, clear up to over 100,000 centistokes at 40 degrees. So you're really looking at different types of open gears for different kinds of applications. Climate can change things, what the ambient heat, and obviously the pressures and the speed.
Yeah, and maybe just to jump in for a little bit of context as well. I mean, most of the time when we're talking enclosed gear drives in industrial, the viscosities that you're typically talking about are, 150 to 680 centistokes
Mhm.
at 40 degrees Celsius. So anything in that sort of like 10,000 to 100,000 range is, off the charts in terms of gear oil viscosities.
Yeah, it's probably important just to, in your mind, conceptualize, as Bret said, in an enclosed gearbox, it's exactly that. The lubricant is enclosed. In an open gear environment, you cannot enclose the lubricant. So it's all about keeping the lubricant on the gear, but it's not in an enclosed environment. So you've got to find ways to, or the formulators have to find ways, one, to get the lubricant onto the gear set, make it pumpable. They need to keep it on those gears for as long as they can before it gets replenished, because ultimately it's a lost system. If it's not a circulating system, the lubricant is not contained. So it's about keeping the film condition at the best optimum level you can. And that is different for an open gear on a piece of mobile equipment, because consider a shovel in a pit. You can't have a lubricant dripping off all over the machine. So you would typically really look for a grease type of open gear lubricant. Whereas on a rotating ball mill, you have more options because you can contain your cycle of lubrication better. So it's all about how do you keep the lubricant where you want it to do the job that it needs to do.
Yeah. Yeah. Awesome. I mean, you already touched on there a little bit, and that's probably a good segue into one of the big kind of like, I guess, divergences in open gear lubrication, which is, do you select an open gear lubricant versus an open gear grease? Would you guys be able to talk through some of maybe like the decision points about what drives you towards grease lubrication versus, fluid lubrication in some of these gear sets?
Lars nailed it on the head. He said the mining equipment in the pit versus the mills. Typically on the mobile equipment, you want it to stay there as long as possible and really adhere to the gear and stay put, but you still have to replenish it. On a mill, you want it to remain mobile, fluid. If it starts to solidify too much in the root of a of a gear, then you're going to cause some severe problems. So that's the first question to ask: is it rotating the same way at a constant speed, or is it a unilateral gear? Um, eh, Second question would absolutely be, what's the climate? How much temperature and then you start getting into a couple other details.
Yeah, it's important also to understand typically, it's possible to define open gears or open gear lubricants into probably 3 or 4 different categories. So we generally talk about a grease or a fluid. It splits down a little further than that into a grease, into a fluid, into a residual, into an oil. So there are various ways to define the type of lubricant, but typically a grease type is really what's used on a horizontal open gear on mobile equipment and can also be used on a rotating ball mill type application. The reverse is not true, however. A fluid type of OGL typically cannot be used or should not be used and is not used successfully on horizontal open gears on mining equipment. So greases, I guess, are more functional in terms of the range of applications, whereas I would say a fluid type or an oil type is more restricted to a rotating vessel type of open gear application. So that would be the first way to decide what is the right type of product to select. But it goes beyond that, because as Bret touched on earlier, you have 2 types or you have 3 types, but generally in practice, we have 2 types of lubrication environment. One is boundary lubrication. The other is hydrodynamic lubrication. Hydrodynamic lubrication would be the preferred status to lubricate 2 gears, but that is not possible on horizontal open gears on mining equipment. So there we typically have boundary lubrication conditions where we need solids and we need greases and we need a tacky product to provide that lubrication. Whereas in an open gear or on a ball mill, you have a little more flexibility in terms of your choice in certain respects as to what type of lubricant you can choose in terms of a fluid or an oil type lubricant, if that makes sense to you. We're also driven by OEM requirements. So OEM requirements often dictate the type of lubricant. So if you look at your mining, your traditional mining shovels and drag lines, that's already clearly specified by the OEM what type of product he wants, so or they want. So that pretty much defines the range of products you can offer the customer. When you go to a ball mill, the same thing applies. You would have OEM approvals and specifications that would lean towards other types of technology. So it's driven by a bunch of those criteria. Often it's around what does the customer want and what do we want to give the customer to meet his requirement? Because at the end of the day, we want a sale, but we also want to give the customer the best product we can give him. If we could convert everybody to the best solution, we would. That is not always possible. So we try to give the customer the type of product he wants or needs. And if we can get him to a better type of technology, we do that.
Yeah, really interesting. Now, maybe if we start specifically and drill down a little bit into the greases, you already mentioned some of the applications where we would use greases over a standard fluid lubricant, if you want to call it that. I think it might be helpful for people to understand a little bit more about sort of what kind of greases are applied. You already mentioned solid lubricant, and I think anytime you say that, people's mind jumps immediately to moly. But there's probably a little bit more to it than that. So are you able to give a little bit more information on the types of grease thickeners? What's the typical base oils we might be using? What kind of thickness and what kind of solids are often used in these applications?
So first thing is, it's technically a grease, right? Like an open gear lubricant that's a grease type is technically a grease, but it's not compatible with greases. So if you put an EP grease on top of an EP OGL grease, they will wash each other. They don't get along. An open gear grease is its own animal. And there's a few different thickeners that are you see common in the market. Just like with EP greases, you'll see a lot of lithium. You'll see some aluminum. Aluminum's pretty popular just for the pumpability issue. You're starting to see a little bit of calcium sulfonate in that space for obvious reasons. Calcium sulfonate's a great thickener, but they're much thinner than you would typically see in an EP grease. the AP greases that most people have. Any cartridge is going to be an NLGI2. You won't typically see an open gear lubricant at more than an aught. So an aught, a double aught, a triple aught, depending on how thick, how much diluent. We'll talk about diluents, I'm sure, as we start talking about the OGLs. And you're really looking for the characteristics that they bond to a gear, to the metal. And you can put too much on and it'll wash itself on. It doesn't get along with others because it'll wash off. So application rates and the timing of the application, how you apply it, how much you apply it, are critical to the success of anybody's open gear lubricant. So there's not near as much thickener in it as there would be in a normal grease because you are going for those aughts and double aughts.
Yeah.
I think you got it all. And again, it's about pumpability in different climates. So it's about base oil viscosity. Obviously, the soap, that the choice of soap gives certain properties, whether it's water resistance, stability under shear. So all of those characteristics are important in terms of the types of soaps. But generally, as Bret's mentioned, aluminum complex, lithium complex. We have some bentone clay products too that are an older technology thickener, but still very functional. And still we sell a lot of those types of products in the market because they have specific properties. So any of those three types of products, typically, if you look at a lot of shovel approvals, you will find that they would approve more than one type of thickener. So it's just important to note that not all of these are compatible with one another. So they are not readily interchangeable. And as Bret says, an EP grease is not compatible with an open gear grease. They are different animals. They are formulated differently. Again, if you consider what the machine is doing in a pit that's dusty and there may be moisture and snow. I mean, I've seen shovels in minus 20 degree conditions in Siberia. I've seen them at 40 degrees C in Africa. So the performance of that lubricant has to meet the requirements of the environment. It has to carry the load. And so the choice of soap and the choice of thickener and other additives is what one would consider depending on the environment and the piece of equipment.
Yeah. Awesome. And just in terms of solids, is it the usual suspects? Like, is it, moly and graphite kind of all the way, or do we see anything else?
Moly and graphite, you'll see some calcite too. Calcite and Teflon here and there, but not a lot. But one thing that I wanted to bring up, Laurence touched on it, is the compatibility part of it. When we're talking about grease compatibilities, everybody knows what the fear is, right? You're gonna put the wrong greases together; they're gonna form almost an epoxy and start very bad things will happen. You have those concerns to OGL, but above and beyond that, on an application side, almost no OGL is compatible with another because they're trying to bond to that metal and they're both going to fight for position to bond to that metal. So if anybody's got open gear lubricants and that's watching, you always have to, the way you handle changing a product, it can be done but there's definitely a different type of process to follow compared to a grease. And it's, you flood the system and then you thin it out because, again, application rates are key.
Yeah. Yep. And this is where I guess contact your local expert comes in pretty handy because I think, a lot of people, I've personally seen a couple of really bad situations where that changeover has gone
it's easy to
horribly wrong.
Contact your local expert is a very good bit of advice.
Yeah. All right. So that's a little bit on greases. And if we move into the fluids, open gear lubricants as such, it would be helpful, I think, to understand a little bit about why these are different from standard industrial gear oil. So as an example, when you look up tables of open gear lubricants that are available, often they sort of get divided into the, let's say, very high viscosity synthetic style open gear lubricants. And then you've also got your sort of asphaltic lubricants. Now, in the industrial world, we're used to dividing things typically by, mineral paraffinic and synthetic PAO style lubricants. And so to see something that's asphaltic is is very foreign to people who are used to dealing with lower viscosity industrial lubes. So one of the obvious questions would be, why aren't we using just standard, mineral oil lubricants, but at much higher viscosities? Like, what's the restriction there?
I'd say the biggest restriction is the cost of boosting the viscosity. I mean, when you start talking about, you said it before, your typical gearbox, you typically don't see much over 680. Well, most industrial plants won't see anything over 320. And ours, when you start talking about compounds or asphaltics, you're automatically in the 10,000 range right there. So, asphaltics were used because they were generally a thicker viscosity. There's a lot of asphaltics is an older technology. It was used a lot in the market because it was cheap and it was already that type of viscosity. And it's a messy, dirty, ugly fluid, but it also has a lot of open chains. So it's very easy to additize. You can go along with it, but it's cheap. So you can use a lot of it and it's still cheap, but there's some environmental issues with asphaltics. It is older technology. But I think the biggest thing is that the health and the environmental issues is why the industry as a whole is going away from asphaltics.
Could you please help describe a little bit more about those health and environmental issues?
Yeah, aromatic groups, aspartame, various other carcinogenic causing substances in their structure. So essentially they are, well, not potentially toxic, they are toxic. So, for anybody operating in the environment, they are exposed to a toxic product. But yeah, absolutely, aromatics, other carcinogenic substances that are clearly no longer acceptable in 2023.
Yeah. And then it stands to reason, obviously, when you're having to dispose of that product at the end, it also requires its own kind of segregation to ensure that it doesn't end up
Correct.
in, waste streams where it shouldn't.
Yeah, asphaltics, I mean, that was an early technology, chosen for the reasons I think Bret described: readily available, cost effective, good viscosity options, easy to put additives into, all of those good things. And they still perform very well up to a point. We still have customers that buy those products, even though we are moving towards phasing them out where we can. But yes, they are toxic. So toxic to people in the environment that are clearly exposed to those products. They are difficult to dispose of because, as you mentioned, they need specific disposal methods, and that's becoming expensive and inconvenient. And then they have some practical things that make them less attractive. So they do build up in the roots of gear sets, and that can be problematic. They harden in the gear guards. They drain slowly. So practically they tend to be messy and provide some maintenance issues. Let's put it that way. So if you add up all of those three negatives, there are technologies that allow us to move away from that now and have less toxicity, more environmentally acceptable products, and practically more functional products.
Yeah. And I guess just to highlight the issue of build up in the tooth root, for people imagining that sort of that gear mesh, if you get enough build up of that material in the tooth root, it starts to sort of like push against the intermesh between the gear teeth, right? And starts to add stresses to the system that you might not want.
100%.
So when we're talking about the synthetic style base oils, I think, let's say 99% of the time in industrial, we're talking about polyalpha olefin style synthetic base oils. And obviously you've got the occasional polyalkylene glycol for worm gear drives and things like that. What kind of synthetic tends to be used in the open gear synthetic lubricants?
Group 3 and Group 4. I've never seen a PAG in an ODL. There may be a PAG for some food grade stuff, but that's not really my ballyhoo. But it's always a Group 3 or Group 4. And again, high viscosity, you have to use much less of it, and it's a lot more environmentally acceptable. When you start talking about your group threes or group fours, then you can dispose of it with your waste oil. The way your waste oil and your hydraulics oils, they'll break down, and that even though they're that really high viscosity, there's going to be so little of it compared to your typical waste of hydraulic oil and gear oil that it'll dilute it enough to get rid of. But the newer technology on the synthetics is it's beautiful technology. You've got these big massive gears that are running in mesh, and you're keeping them in a hydrodynamic or a full fluid film by getting the viscosity right. Now, when we're talking about bearings, we start talking about 68 centistole. But when we're talking about these high viscosity synthetic gear oils for gears, you've got a 12,000 centistole oil that's keeping two gears completely separated, and as long as they're in that right speed and nothing slows down, and not a startup obviously, but they're really running in a full fluid film, and you can see life extension on the gears, energy savings, and what Laurence is talking about, balancing a mill with load. We've seen mills actually be able to increase their load because of the reduction in friction on the gears. So it's pretty amazing technology.
Yeah, that's amazing. Maybe one obvious question that the audience will have, and this is where we can start to talk about diluents and things, would be the pumpability of such high viscosity lubricants. So, my own experience would be, once you get to about 30,000 centistokes or whatever, it's actually hard to get this stuff out of the drum. It's just, it's like treacle, right? It's like this very, very incredibly thick honey, and it doesn't readily pump. So what is the role how do you pump a lot of these lubricants, whether it be the asphaltic styles? We already talked a little bit about the greases and the very, very high synthetic, very, very high viscosity synthetic gear lubricants. Maybe we can talk a little bit about pumpability as well as like application style as well.
Yeah. So typically, diluents are exactly there for the reason you mentioned, because if you have 100,000 centistoke base oil starting oil for your OGL, that's not a pumpable product. So clearly we want the high viscosity, but we've got to also practically be able to get it into a drum and out of a drum and pump it onto the OGL through a lube system, or onto the open gear through a lube system. So the primary function then of the diluent is to bring the viscosity down to a usable, pumpable scenario, to something like 3.5 or 4,000 centistokes, for example. That's pumpable in most ambient conditions. Yes, we have lighter grade products for lower temperatures, but really the diluent is just to keep it in a drum. We can get it out. We can pump it through a lube system without having to use heated belts and blankets and other more complex things to make the lubricant pumpable. Get it onto the gear set. Once it's on the gear set, obviously everything changes, because depending on the nature of the diluent, it will evaporate, it will volatilize. It's done its job. And then you get a viscosity change on the gear set, and obviously viscosity and film ball will follow. So the only reason really for the diluent is to make it practically pumpable and to get it onto the gear set. Now, having said that, there are different types of diluents. We use less of a diluent, more of a low molecular weight spindle oil, because there are some environmental challenges on diluents. Some are more acceptable than others. Like everything, one has to be aware of what you use. In our EnviroLube XE type products, they are all non-asphaltic products. They use a diluent. They have 100,000 centistoke base oil viscosity, but in the drum, and as we supply them to the customers, depending on the grade, between 3.5 and 4,500 centistokes. So very usable, very pumpable. And then interesting mechanism, once the diluent, let's call it, that has volatilized, you get a viscosity climb. So what you're getting is a film viscosity build on your gear set. And I mean, we estimate on our EnviroLube XE products, which are very special types of products and technology, anything from a 15,000 to a 20,000 centistoke film thickness in an operating gear set. So rather than having a drop in viscosity with temperature, we get a rise in viscosity because that is how our product is designed. So that gives you a much stronger film, that gives you a much better hydrodynamic condition. And we have also seen from experience, and we've documented that we are able to, in some cases, not all, so in some cases, we have seen reductions in vibration on ball mills and gear sets, which we attribute sometimes to the strength and the viscosity of that film. So it is able to absorb a certain amount of vibration. We have seen reductions in vibrations because of that film strength, that film thickness, and that mechanism of diluent.
Yeah, that's really interesting. Maybe the other broad category of, let's say, open gear lubricants or fluids or whatever you want to call them would be the huge variety of running in compounds that are on the market. Now, I know different companies have different perspectives on this. So could you help sort of describe maybe what's the purpose of them? Because when people say running in, like, we don't typically have running in compounds for industrial gearboxes, right? When people hear running in lubricants, often they're thinking about an engine oil. So, what is the purpose of some of these running in compounds, and how exactly are they supposed to work?
So when you've got an enclosed gear case, you've got it from one manufacturer, right? And those gears are paired. So you've got a machine process that's already happened. When you're talking about open gears, you're replacing gears. A lot of times the gear will be made by two different manufacturers. They're definitely not a paired gear set. There's a pinion and there's a bowl, but they're not a paired gear set. So you have to, when you're talking about break-in, you're really trying to control wear. So there's going to be wear, but you want to dictate how the wear happens. So you're basically taking the asperities and trying to match the asperities so that the asperities don't cause excessive wear and shorten the life of a gear set. So you're controlling the wear to a certain extent, knocking off the tips of the asperities. Again, this is when you want to consult your local expert. A lot of companies make products with something like a ZDP where it's not over anodized. So you do have that break-in fluid within the fluid. Some others will recommend a break-in fluid with an aggressive additive package, but you really have to monitor it and know what you're doing, because I keep talking about wear, and we don't want our gears to wear. So you want to control that wear in the right way, have an additive package that activates with heat. So then it's not an aggressive, but then there's other people that make break-in fluids that is not dependent on heat, that is very aggressive, and you have to know what you're doing and how long to run it, and can you run it loaded, unloaded? There's a lot to get into.
Yeah, right. So maybe just to add to what is happening there, as Bret mentioned, so you've got two gear surfaces that are not a matching set, let's put it that way. And at a microscopic level, the pinion and the bull gear have surface imperfections and asperities on the surfaces. Obviously, those are colliding and clashing before that gear set settles down. That is not a good environment because you're breaking pieces, you are generating wear. So obviously what we're trying to do with a running in compound is, in a controlled fashion, get through that running phase as fast as we can in a controlled way to remove those asperities, because what we're trying to get to is two flat, smooth surfaces, because that allows for greater load carrying capacity compared to two surfaces with peaks and troughs, which never really fit together well, and the load carrying capacity is limited. So that is what the running compound is designed to do. It's designed to smoothen those surfaces, and there are different chemistries that do that. However, it's something that has to be a managed and controlled process. If I can jump in and use a little bit of license here, Whitmore is not a great proponent of running in compound. So we have a lot of competitors that would recommend a running in compound and then change to a running OGL thereafter, which obviously involves some process changes and stops, etc. So our technology includes quite clever chemical additive packages where we do not need a running in compound. Whitmore, I should say, has additive packages that immediately will allow for that smoothing process to take place. So we talk about we used to use the word eutectic technology. We now refine it to microslide technology, but what it really is additive packages that are induced or basically become active at high temperature, as Bret mentioned, where you get collisions between those high points. High temperature generates a chemical reaction, and you get a chemical reaction between the additive and the metal surfaces, and that results in a coating on the metal surfaces and almost a plastic metal flow. And that results in a smoothing of the surfaces and ultimately better load carrying surfaces for the two gears, and which is what we're looking for. So our technology allows us to go straight to a running in. Sorry, let me repeat that. Our technology allows us to go straight to a running lubricant. We don't have to use a running in compound of any kind. We go straight to the regular product, and that will provide smoothing of the surfaces within 200 to 300 hours. We also and it's fascinating technology. It's what they call organometallic reactions that are taking place between the additive packages and the metal surfaces. And we regularly document surface improvement on gear sets. So typically we try to look at a gear set before we change to our product. We document, we take pictures, we take temperature readings, etc. But we have been able to document surface improvement of imperfections on gear sets after several hundred hours of using products that has this additive technology. So it's fascinating stuff, but it's the same thing we're talking about running in. It's all in one product, but it's essentially trying to flatten the asperities on the gear sets.
Yeah, so maybe just to make the distinction there. So with most of the running in compounds, which are kind of chemically active, I think what you're basically trying to achieve is a controlled chemical version of wear with something
Correct.
like an EP style additive or a ZDDP style, phosphorus additive. Whereas what you're describing there is more of something that is a kind of a plastic deformation technology, right? Where there is not actually any removal of material, but rather a reorganizing of the metal surface.
Correct.
Okay.
So we approach it, or the technology, the technology approaches it from a chemical reaction with the metallic molecules at a micron level, a plastic flow, and a rearrangement, let's call it, of the shapes of those asperities. So you get less conflict between asperities, smoother surfaces, and you get to a hydrodynamic situation faster. So that's exactly what it's doing.
Yeah, interesting. Whenever I start to sort of wrap up these interviews, I always like to take a bit of a look to, the future and what happens over the next, 10, 20 years. Obviously, our industry doesn't move crazy fast, but there is always new technology being developed in the background. Between the two of you, do you see any emerging technologies on the horizon, or maybe there's even a technology that you think would be, really a really great application? Is there anything that you see on the horizon for open gears?
I think there's going to be a lot of environmental drivers. Our whole industry has been moved by regulations and environmental concerns. So most open gear lubricants they're total loss lubricants. And as much as we want to do the right thing for the environment as well, and all of our customers do as well, we have to be conscious price. I can see some more environmentally friendly things coming down the road, and try to be more sensitive to Mother Nature. And then also you're seeing some different thickeners come into play. And I'm excited to see what those are going to develop into for open gear lubricants.
Yeah, just to add, I think Bret's right. I think all the development will be around making nicer products that are more environmentally friendly. So that'll be important. We know that our customers are moving in some respects to high viscosity, or we see a trend to high viscosity fluid type products without a diluent. So that's another direction. This thing of a transparent OGL versus a water white one, that's been around a long time. I don't think that's going to change. I think as long as the technology allows you to inspect and it's a practical solution, that's probably not going to change significantly. I think lower consumption lubricants clearly would be a consideration, because mining companies and operators of assets like this want to spend less money on lubrication, and they want better performance. So it's going to be a combination of environment, lower consumption, softer on the planet. And I think the additive suppliers will continue pushing the boundaries with their additive technologies. But I certainly don't see any significant game changer. I think we're already at a place that meets where ball mills and open gears are. Our technology will be driven by, how do open gear requirements change? So do they get bigger? Do they get smaller? Do they get faster? And the open gear lubrication will evolve around the requirements of the OEM and around the equipment that we're trying to lubricate.
Really interesting. Well, gentlemen, thank you so much for your expertise that you're bringing to the table, because open gear lubricants is certainly one of those ones where the kind of like the service offering is hugely valued. I know, among especially like the mining customers and that, because it does require, let's say, a higher level of expertise to be able to, select and apply them in the correct manner. So, really appreciate your time. Thanks so much for sharing your insight, and hopefully we'll talk again soon.
Thank you
Great.
for the
Thanks,
opportunity
Rafi.
to talk to you. Appreciate it.